Hello to everybody. I am really happy to greet today International Conference, all the participants of the International Conference on Science and Technology Research. My name is Lyudmila Gryzun. The topic of my keynote presentation is exploring the properties of polygonal numbers and their educational applications for computer modeling. I am happy to represent today here National University of Economics, Kharkiv, Ukraine, where I work as a full professor of Information Systems Department. I earned master degree in applied mathematics from the State University of Kharkiv City, Ukraine. I also earned PhD and second doctoral degree in pedagogical science. My recent projects you can see on the screen, among which there are keynote presentations at Eurasia Research International conferences during last 2 years. The focus of my current research activity is holistic educational approach to different specialist training. And the topic of my presentation and of my research is not occasional today, and you'll understand in some minutes why. During my presentation, I am going to represent our mathematical results of polygonal numbers investigations, and also in the second part, I'd like to cover the ways in which these and other results might be used in education and in its holistic content. Various educational studies conducted recently across Europe confirm decreasing interest to mathematics and lack of students' motivation to master it, because mathematics seems to be too abstract for students and too far from real-life tasks. We can distinguish two main contradictions today between urgent needs of society and to raise level of mathematical education and falling students' motivation to learn mathematics deeply, between great cognitive power of mathematics as a science and insufficient using of this power in the educational process. In order to resolve these contradictions, it's necessary to propose relevant didactic mechanisms, to apply computer technologies and make mathematical concepts serve educational purposes such as creating students' mathematical outlook and culture, demonstrating them practical value of mathematics and raising their interest to it. In this context, the phenomenon of polygonal numbers seems to be a really bright example of both cognitive resource of mathematics and its application to didactics and to real life as well. Actually, we can see polygonal numbers in nature and daily life everywhere. For instance, in honeycombs, spider's web, packed eggs, and so on. However, these numbers as a mathematical notion arose long before our era, as a result of formation of the natural numbers series composed from the sums of arithmetic sequences. And ancient scientists gave elements of this series this or that geometrical interpretation. In particular, they considered them as sequences of regular polygons made of dots. Among ancient scientists who wrote about polygonal numbers, we can name Greek mathematicians Diophantus from Alexandria, Nicomachus of Gerasa. Later relations between natural and polygonal numbers were investigated by great mathematicians such as Fermat, Leonhard Euler, Augustin Cauchy, and others. However, the analysis of scientific and popular scientific literature testifies that a lot of interest and relations between flat polygonal numbers didn't obtain detailed research, and some known relations can be generalized and proved by modern mathematical methods. On the other hand, polygonal numbers as a mathematical concept obviously have significant educational value. They allow students to realize a link between geometrical and algebraic essence of a number, to trace the continuity of geometry and algebra methods in mathematics, and to see applications of abstract notion to practical problem solving. Thus, investigation of various properties of polygonal numbers, as well as finding didactic ways to apply their pedagogical potential, seems to be urgent and topical. Our research focuses on some main objectives: to obtain and represent some relations between flat polygonal numbers based on their properties investigations, to determine binary algebraic operation on the sets of polygonal numbers of various angularity, and to investigate algebraic properties of the polygonal number sets, and definitely to represent authors' computer models of polygonal numbers and the ways in which these and other results may be used in education. In order to achieve the objectives of our work, we used the method of analysis of common definitions of polygonal numbers, the polygonal numbers table, methods of algebraic transformations, basics of the algebraic systems theory, and apart from the theoretical methods, we also applied instruments of GeoGebra software, MS Excel, to build and investigate relevant computer models of polygonal numbers and their series. We are starting from some common definitions. Let us consider a sequence of regular triangles composed from dots. If we agree to consider the first left dot to be also a triangle, then on this figure you can see 4 members of this sequence. We will put it correspondence to each triangle, the number expressing the whole amount of dots in each triangle. In such a way, we obtain numerical sequence, which you can see on the screen. These are triangular numbers. If to designate them 3 indexed n, where n is the index of a member of sequence, and digit 3 specifies that numbers are triangular, it is obvious from the picture that the first triangular number is here and equals 1 dot. Second triangular number is here and it is 1 plus 2, and so on, and the third one, the fourth one, etc. Obviously, the nth triangular number is the sum of n first natural numbers, and its formula is shown here. Quadrates and regular pentagons are similarly considered. Thus, it is possible to receive any polygonal numbers in such a way. All polygonal numbers can be put in the infinite table with the general formula of the nth index of the series of k angular number. So the general formula of k-angular number with index n is here, where d is difference of arithmetic progressions and equals k minus 2, where n is index of the k-angular number. Coming from these theoretical basics, we obtained a number of results. Most of them are relations among the polygonal numbers based on their properties investigation. Our first result is the general formula of difference between k-angular and k-1 angular number with the index n. Based on this formula, n's, we obtain general formula of calculation of any k-angular number with index n, where n's triangular number and definite quantity of differences are n's. Our next result is the relation between nth pentagon number and quadrate number with index n minus 1, which was obtained based on the analysis of series of pentagon and quadrate numbers. You can see this generalized formula on the screen. Some relations were obtained on the base of the known Diophantus relation for triangular and quadrate numbers. In particular, the connection between the indexes n and m of triangular and quadrate numbers accordingly was established for the Avantos relation. So the Avantos formula was generalized in such a relation, which you can see on this slide. Geometrically, it can be represented in such a way. The dots matching in its amount a quadrate number indexed m equals 2n plus 1 form a quadrate in total. One point is in the center of the quadrate, and the rest of dots are grouped together in the form of 8 rectangular triangles with broken hypotheses. Each triangle contains the amount of dots matching a triangular number with index n. Furthermore, intuitively from the geometrical ideas, we also concluded such a relation. We a bit generalized our previous formula. Based on the previous relation, analysis of the table of triangular and pentagon numbers, and from geometric reasons, the relation between triangular and pentagon numbers was obtained. Really, intuitively, it is clear that from quadrate and 4 triangles we can build a pentagon. We checked this fact algebraically for triangular and pentagon numbers with different indexes and discovered the following regularity. From here, the relation between triangular and pentagon numbers appears, and you can see it also on the screen. Geometrically, it means that from 12 triangles, each of which contains the amount of dots matching nth triangular number and one more dot, we can build a pentagon. It will contain the amount of dots matching a pentagon number indexed to n plus 1. However, n dots, here there are 2 of them, will be extra and they will not be included into construction of the pentagon. So the similar geometric interpretation you can see here for n equals 3. All obtained relations were proved with algebraic methods. Here we summed up possible applications of the obtained relations. They might be used for determination of maximum amount of equal figures located inside of specific shape, degree decreasing in number series, time series smoothing, and other. Our next portion of results is connected with determination of binary algebraic operations on the sets of polygonal numbers of various singularities. The following results were obtained on the base of the algebraic systems theory and the analysis of the polygonal numbers series. We considered polygonal numbers on the angularity k as infinite sets and based on the definition of binary operation of a set. As a result, we obtained the following: that at addition of 2 arbitrary k angular numbers, k's and km's, in order to receive the third number of the same angularity, it's necessary to the result of the traditional addition to add the product k minus 2 multiplied m multiplied n. In order to prove this, we used the common formula of k-angular number with indexes n and m respectively. So, in such a way, we determined the binary operation of addition on the set of polygonal numbers with angularity k. Here you can see geometric interpretation. The result of the obtained addition operation is the number of the same angularity with an index equal the sum of items indexes. Thus, the binary operation of addition is invariant in relation to the angularity of numbers. So when we add 2 triangular numbers, we obtain in total also triangular number. If we add two quadrate numbers, we obtain in total also quadrate number, but of different indexes. Also, the binary operation of multiplication on the set of polygonal numbers of arbitrary angularity also was obtained, and you can see it on the screen. As on the sets of polygonal numbers of angularity k, binary operations of additions and multiplications are defined, these sets can be considered algebraic systems. We also proved that the defined operations of addition and multiplication submit to commutative, associative, and distributive laws. Algebraic properties of the polygonal number sets as algebraic systems were investigated. In particular, it was established that the set of polygonal numbers of angularity k are not groups in relation to the binary operation of addition. They are not also groups in relation to the binary operation of multiplication, and they are not groups, they are not rings in relation to the binary operation of addition and multiplication. Obtained results and the algebraic properties of flat polygonal numbers pushed us to use them as fruitful material for involving students into research and constructive process of mathematics learning. First of all, we constructed our own dynamic models of polygonal numbers in GeoGebra environment and developed special didactic support in order to encourage students to make independent conclusions as for these numbers formation and composition of their series. For example, we suggested students answering such a chain of questions based on the work with the models. For example, the questions: what happens with the amount of dots on each side of triangle? How many dots on each step are added in total, and one, and so on. So we allowed students to combine in one model numbers of different angularities and manipulate with them to check obtained regularities and find out their own ones, and then to prove them algebraically. Experimental work with ready-made models of polygonal numbers is only one way to cognitive activation of students. We would also recommend so-called constructive way to use polygonal numbers phenomena in order to progress students' motivation. It is based on the idea of encouraging students to build similar computer models themselves. The matter is that it is easy to obtain the total amount of points algebraically. However, it might be a challenge for students to locate proper amount of dots in proper shape of a regular polygon and to automatize this location using GeoGebra tools or to develop a computer program to obtain proper polygons. Moreover, polygons must be geometrically similar and they must be overlaid in order to contain total amount of dots. Here students bump into necessity to figure out proper regularity and to find out the way how to visualize this irregularity using a computer. So it's a learning challenge for students. We would suggest a sort of pre-teaching in order to push students to their discovery. So we offer the chain of the questions. For example, if we have a point coordinated mn, how should we change these coordinates in order to make them form on each step new quadrate or triangular number? What will happen if we fix m and change n with some step, and so on. Here we can also relevantly introduce sequence function as important built-in GeoGebra tool, and repetition, and so on. Finally, it is also really beneficial to encourage students to build so-called a universal model for polygonal numbers of any angularity, as it is connected with some practical geometrical problems of points location on the plane. Here we would offer students the following chain of subtasks. One of them is the task of placing key points around this circle where k is the angularity of a polygonal number, and to elicit from students the proper angle of rotation and the list of obtained rotations. It might be also the task of repetition of the list of the obtained rotation according to the index of a polygonal number, and so on. As a result, students come to the nested construction of sequences and elements of list. They use sequence function and list function of GeoGebra software and can manipulate it to verify some theoretical regularities among polygonal numbers. In addition, we can encourage students to build two universal tables using, for example, MS Excel spreadsheets in order to verify and demonstrate the action of binary algebraic operations of addition and multiplication on the sets of polygonal numbers of various angularities determined above. After manipulations with the universal model and tables of the binary operations built by students, we can emphasize nowadays implications of polygonal numbers and get students familiar with those practically urgent tasks where polygonal numbers themselves and their constructed dynamic models might be used. Among these applications, we would like to emphasize the problem of determination of maximum amount of equal figures located inside of specific shape and its derivation, the problem of dense package of balls inside the shape. The method of time series smoothing based on polygonal numbers usage and applied to investigation of indicators of funds markets. Also, it is genetic algorithm modified based on polygonal numbers, location of cell connection towers, and other tasks. According to the aims of our work, they were obtained and represented some relations among flat polygonal numbers based on their properties investigation. Binary algebraic operation on the sets of polygonal numbers of various angularity were determined, and algebraic properties of the polygonal number sets were investigated. Dynamic computer models of polygonal numbers were built in GeoGebra environment, and the ways in which these and other results might be used in mathematical education were determined. In a whole, obtained results may be considered as a didactic support of mathematics learning, computer science learning, and computer modeling. Summarizing our research, we can come to some conclusions. We can theoretically predict that using our results for mathematics and computer science teaching and learning, we will be able to provide some benefits for students. The most important of them are bringing up students' holistic view at our world, integrative understanding of algebra and geometry, as well as realizing integrative role of mathematics as a universal language for reality description. Another educational benefit is forming students' philosophical and historical outlook, as polygonal numbers are presented to students as a really bright example of historical continuity. Then can trace historical roots of the concept itself and transformation of its practical applications. Apart from integrative and philosophical outlook, with the help of our didactic tools, we will be able to develop students' skills of recurrent relations obtaining, necessary for their algorithmic thinking forming. We can also develop students' modeling skills, as we encourage them to build dynamic computer models of mathematical objects and to manipulate them. As a result, we can expect a raising of students' motivation and interest to scientific learning and exploration. Didactic tools presented above might be used both in curriculum and extracurriculum studying of mathematics, computer science, computer modeling at high school and university. They also can be interesting for teachers, including pre-service teachers. The full results of our research are published in the Journal of Physical and Mathematical Education, and they are available in the internet. Here, really thank you for your attention, and I am ready to answer your questions.